Okay, so let's look at this exercise here. So this is my own solution. I'm sure there are many different ways that one can do this. So I thought of this statement that we have the ciphertext UV encrypting a signature on a message M as an equation over some variables. So the secret variables I introduce are the signature sigma, some help element F, and some randomness R used in the encryption. So, so there will be a pairing product equation defined by the verification of the signature. So that's what I have over here. So the pairing of the signature with the W, the public key of the signature scheme, and H to the message. And that ought to be the same as the pairing of G and H, but I have moved G and H to the other side, so F will be G inverse. And the reason I've done that is because there was a condition when we looked at pairing product equations that they should give you the result 1, not just some arbitrary element in the target group. There are technical reasons for that, so I'll get back to that question in a moment. Okay, so then you have the multi-exponentiation equation. So basically this is just to make this be the same as the verification equation for the signature scheme. And then I'm saying that the first element of the ciphertext should be G to this secret R. And the second element of the ciphertext should be the public key raised to the secret R multiplied with the signature, right? So this is the plain text of the ciphertext. So taking together these 4 equations, 1 pairing product equations and 3 multi-exponentiation equations, guarantee us that we have actually encrypted a signature on the message M. Okay, so I should perhaps mention that if you write out this equation here in full, so actually a multi-exponentiation equation is over a bunch of unknowns and knowns, known group elements in G1, known field elements in ZP, and these exponents gamma ij. So if you want to write all that kind of stuff out, what you get is these kind of elements here, and you could write the equation as something like this. And you will see that this is on the form that corresponds to a multi-exponentiation equation, right? So the target we would be hitting at is G inverse. That's here. That's a known element. Okay, and then we have the unknowns. We have the unknown R. We have the unknown F. And we have the unknown sigma. Okay, and we do various things to those. So we can take the unknown R and match that with a known group element, in that case just 1, so it cancels out and we ignore that. Okay, we can take the unknown sigma and match that with a known exponent, so we'll take 0 here, so that cancels out. And then we can take the unknown F and match that with a known exponent, so that's the 1, so that gives us our F to the 1. And then we take the unknowns with unknowns, so sigma to the unknown exponent R. And since that doesn't appear over here, we just set that gamma 1 value to be 0, right? So then that cancels out. And we have the unknown F to the unknown R, again with a 0 exponent, so it disappears. So if you write it out all generality, as I had on the previous slide, that's kind of the variables and constants and knowns that you plug in, that gives you what corresponds to this multi-exponentiation equation. Okay, so what this shows is that we can actually encode relatively efficiently a practical statement with these equations, right? So we had this practical question. Here's a ciphertext. Does it encrypt the signature in the message M? And we can encode that with 4 equations. Okay? Now, my next claim is that we can actually construct efficient, non-interactive zero-knowledge proofs for these types of equations. Okay, so that's where we're going next. How do we actually prove that these equations are true and that these equations are simultaneously satisfied? And I'll start with a warm-up proof system that doesn't give you so much privacy, but it does give you perfect soundness. So this sort of shows where will completeness and soundness in our full Groth-High proofs come from. So I'm going to define first an extended bilinear map. So the map takes now, so we started with a bilinear map that just takes an element from the source group 1 and source element from source group 2 and maps them into the target group, right? So the extended map, and you can view that as sort of an outer product of a pair of group elements from source group 1 and a pair of group elements from source group 2, and I'll map that to the target group in 2 times 2. Okay, so it works like this. When we do this extended pairing of a pair of source group 1 elements and a pair of source group 2 elements, what we do is we apply the bilinear map and get the pairing of C1 with D1, pairing of C2 with D1, the pairing of C1 with D2, and the pairing of C2 with D2. Okay, and we'll use that map extensively, so just want for you to take 5 minutes and convince yourself that it is actually a bilinear map and it sort of works as you would expect. So working with entry-wise products for vectors and matrices, take 5 minutes and check that this is actually a bilinear map. Okay, so let's have a look at this. So we want to convince ourselves that this map is linear on the left-hand side. So let's start with a bilinear map applied to a product of 2 vectors and with another vector. Okay, so this corresponds to, so all of these are entry-wise multiplication, right? So that's the same as a vector with A1, B1 and A2 times B2. So by definition of the bilinear map, that's the same as this thing here, the pairing with A1, B1 and D1, and the pairing of A2, B2 with D1, and then the pairing of A1, B1 with D2, and the pairing of A2, B2 with D2. Now we know that the pairing is bilinear, so we can split all of these into 2 parts, the pairing of A1, D1, and the pairing of B1, D1, pairing of A2, D1, pairing of B2, D2, and so forth, and the same for the second column. Okay, and because we're doing entry-wise multiplication, that's the same as this 2 times 2 matrix multiplied with this 2 times 2 matrix. Okay, so, but by definition, this is actually the extended bilinear map to the A vector with the D vector. And by definition, this is the extended bilinear map to the B vector with the D vector. So this thing here and this thing here, and that shows that we have the linear property on the left-hand side. And of course, the right-hand side is exactly the same. Okay, so now we're ready for a warm-up proof system. So the common reference string will have the setup, so G and H in particular, and also so a couple of random group elements, U in source group 1 and V in source group 2. And I'll look to start with just with a very simple instance, so a single pairing product equation. It pairs unknowns x and y, and the claim is that it gives us some target t. So as I said before, when we want to get zero knowledge, actually this target has to be 1, but at this stage I'm not really concerned about privacy, and it actually works for any general t in that case. Okay, so the prover starts by encrypting x, okay, so later on we will want to have some sort of privacy that will come from the encryption. So the prover encrypts x with LGML encryption, so computes C1 and C2 as G to the R and U to the R times X. Okay, and we will also LGML encrypt Y as D1, D2 being H to the S and V to the S times Y, where R and S are chosen at random. Okay, so at this stage, we've taken our secret variables, we've encrypted them so they're hidden somehow from the verifier, okay, and then let's start doing things with it. And a theme that goes through all of these Groth high proofs is that essentially we do the same thing with an extended bilinear map that we would want to do just with a regular pairing, okay? So in this case, what we really want to verify is that the pair of x and y is equal to this known target t. And what we'll do is we'll just use the extended bilinear map and we'll put in the ciphertext instead of the original plain text. Okay? So we'll take this extended pairing of the ciphertext that encrypts x and apply this bilinear map to that with the ciphertext that encrypts the secret y. Okay? And we'll just do that, do a lot of computations and see what comes out of it. Okay, so the first ciphertext can be written as that's a G to the R and U to the R times X, right? So that's the same as GU to the R times the 1X vector. Okay, and I'll keep the second ciphertext in place for a while. Okay, and we can rewrite that. So we can sort of split it in two by bilinearity, right? So we'll split that in two parts. One has to the GU part and one has the 1X part. Okay, and for the GU part by bilinearity, we can take this R and we can move it over to the right-hand side. So now we have GU paired with this ciphertext here raised to R, and then we have the pairing of 1X with the ciphertext that encrypts Y. Okay, let's continue the calculations. So this part with GU, we'll just keep that and not do anything to it. But on the other part, the 1X part, now let's take the ciphertext that encrypts Y and let's unpack that. So that's the same as HV to the S times 1Y, right? Okay, so what do we get? Okay, so we still have this left-hand side here. And here we have 1X, and we move this S over here. Right? And then we also use the bilinearity to split it in two. So here we have the extended bilinear map to 1X and 1Y. Okay, so far so good. Okay, now this latter part here, right, by definition of this extended bilinear map, that's going to be the pairing of 1 with 1, 1 with Y, X with 1, and X with Y. Okay, and when you pair 1 with something, that just gives you 1. So what you get here is 1, 1, 1, and then you have the pairing of X and Y down in the right-hand lower corner. Of course, this is the target that we're trying to get hold of, right? And then there's all this other stuff here, okay? And essentially, I'm just keeping this other stuff here and this other stuff here, but I am doing a bit of re-randomization, okay? That's where we have this HV to the T, and over here, GU to the minus T. and those two, they cancel each other out. So what I'll do is I'll pick t at random, and I'll take the first component here and multiply that with hv to the t. But then over here, I'll take gu to the minus t, so they cancel each other out. So we still have, this is all equal to each other. Okay, so now I'll have to present the proof. What is the proof? Well, the proof is going to be these group elements. Okay, so there will be this vector with two group elements, d1, d2 to the r, hv to the t. And that's, I'm going to call pi1 and pi2. So that's d1 to the r, h times t, and d2 to the r times v to t. And the second part of the proof will be the component over here, 1x to the s, and gu to the minus t. And I'll call those for theta 1 and theta 2. So that gives us g to the minus t, and x times u to the minus t. Okay? So we get for this equation here a 4-group element proof. Okay? And then we started out by encrypting the secret x and the secret y, right? So that's also 2 elements per ciphertext. So in total, we'll get an 8-group element proof. And the proof consists of a ciphertext that encrypts the secret x, ciphertext that encrypts the secret y, and then a 4-group element proof that this equation that they're supposed to satisfy is actually satisfied. Okay, so let's have a look at the verification of this. Okay, so the verifier, of course, has no clue how all these computations are taking place and what the secret R and S and T is and what the secret X and Y is. All the verifier sees are 8 group elements, okay? An LGML ciphertext in source group 1, LGML ciphertext in source group 2, and then these 4 group elements that it should satisfy the verification equation. Okay, and essentially the verifier will then plug it in. Let's take ciphertext 1, pair that with ciphertext 2, and check that this gives us GU paired with the first half of the proof and the second half of the proof paired with HV, and then times 111 and T, because T is the target that I'm supposed to hit. Right? And all this is sort of stuff that the verifier knows. It knows T because that's part of the instance. And it knows G and U because they're part of H and V because they are in the common reference string. And then it has seen the ciphertext and the proof elements. Okay? So that's all it plugs in, and it checks that this verification equation holds. Okay, so why is this perfect complete? Well, if the proof is honest, does everything according to this, if you follow through the calculations, you see that, yeah, we got all this stuff here, right, with a pairing of x, y. And if the proof is honest, then the pairing of x, y really is t, so we should be getting t here, okay? So the verification will go through if the prover is honest. And the verifier says, yes, I accept this proof. Okay. Now the question is, what about soundness? Is the verifier actually guaranteed from seeing this verification equation being satisfied that it really is the case that the pairing of x and y is equal to t? So, and I'll make that an exercise as well. So I'll give you 10 minutes to try to figure out and convince yourselves that it is actually sound, and if this proof goes through and the verifier accepts, it's because there really is some secret unknown x and y that has been encrypted that pair up to give us t. Okay, yeah, so let me just, Daniel was so kind to point out that I'm missing the s down here, so that should be an x to the s. Okay, let me start with just a point of clarification, since I had a question which is probably good to distribute more widely. So the question was, where would you know those extraction keys A and B from, right? Why on earth would you know that? And there are two ways you can look at this. You can look at this from a soundness perspective. Is this statement true or not? And for soundness, you don't actually need to know them. You just need to be sure that they exist, right? And of course they exist, because G is a generator and H is a generator. So U will be equal to G to some A, okay? And V will be H to some B, okay? So from a soundness perspective, we just need to know that they exist, and if these A and B exist, we will actually be able to show that there exists some X and Y such that they pair to T. You could want a stronger security guarantee from the non-interactive zero-knowledge proof. You could want that it actually is a proof of knowledge, right? In that case, the question is, can you actually, from the prover's proof, extract what is X and Y? Okay, in that case, you would actually need to know what is A and B. They could act as your extraction keys. Okay, and in that case, we would imagine the setup is, when we talk about knowledge extraction, that U and V has been generated as part of the common reference string, so there's some magic third party that appears and says, here you go, here's a common reference string, now you can start making proofs, right? And we say, great, okay? So we start making proofs, we have perfect completeness, everything is great, right? But then we imagine that it's a proof of knowledge in the sense that if we know the matching A and B, okay, suppose this angel that came and gave us the common reference string also said, and oh, by the way, it's A and B, right? Then now it's a proof of knowledge. You can actually use that to extract the X and the Y. So it's a proof of knowledge. Okay, so now let's look at how do we actually get perfect soundness and a perfect proof of knowledge out of this construction here. So we'll define a knowledge extractor that, given A and B, returns the decryption of ciphertext 1 and calls that X, and returns the decryption of ciphertext 2 and calls that Y. Okay? So at this point, it's just some X and Y, but we don't know whether they satisfy the equations or not. Right? So that's the challenge here, to show that if all these proofs satisfy the verification equation, actually this X and this Y, when they pair together, they will give us the target T. Okay, so let's start looking at the left-hand side of the verification equation, right? That will be pairing of the two ciphertexts with each other. And by definition, it's this thing here. Now, if we know A and we know B, then we can try to decrypt the columns. First with A, and then decrypt the row with B. Okay, so let's look at the decryption of the first column with A. That'll be this part here multiplied with this part here to the minus A. Okay, that's what I've written here. And if we look at the decryption of the second column, then we'll take this latter element and multiply that with this first element to the minus A, so that's what we have here. Okay, and we can do a little rewriting because it's a bilinear map, so that's the same as a pairing of C1 to the minus A C2 paired with D1, and the pairing of C1 to the minus A C2 paired with D2. Okay, so okay, now we look at the decryption along this row here using B. Okay, so here we get the first element to the minus B times the second element. So that's the whole thing here. And again, by the bilinear properties, that's the same as the pairing of C1 to the minus A times C2, and D1 to the minus B times D2. Okay, but remember, by definition, this was x, and by definition, this is y. So what we have here is really the pairing of x with a pairing of y. Okay, so this is the left side of the verification equation consists of this pairing here, and now we see that if we take the left-hand side of the verification equation and decrypt in two directions, we actually get this pairing of this secret x and y. Okay, the full verification equation is this one, so we just analyzed the left-hand side, right? But then there were also some proof elements that we had to pair with GU, and some proof elements we had to pair with HEV, and then we had the 111T. Yes, Daniel? Let me just go back one slide. You're saying, so your question is, why did I do all these operations? So your comment is on how I justify doing this? Oh, okay. I think my justification is that it works. Okay, it's not the best of justifications, but at this stage I'm just doing computation and magic things will emerge from it. Okay. Let me try to sort of, after we've gone through all the calculations, to sort of explain what is the intuition there, okay? But I think it might actually be a little easier to see on this slide here what's going on, okay? So, okay, right. So we have three more components. We have this component, this component, this component. So let's have a look at those as well, right? So if you look at this 2 times 2 matrix here, okay? And what it will decrypt to when we decrypt along the columns and then along the rows, okay? Okay, so that will be, so if we decrypt this one along the columns, okay? Essentially what we're doing is we're decrypting this column here. So we'll get U times G to the minus A. That's what we have here. And when we decrypt along the rows, we would get the pi 1 to the minus B times pi 2. And that's what we have here. So that's what it's going to decrypt to with exactly the same computation as we had on the previous slide. Okay? But remember, by definition, U is G to the A. So this thing here, that's just going to give you 1. So now we have a pairing of 1 with something. And that's just going to give you 1. So this thing here just cancels out under this decryption along the columns. If we look at the second matrix, right, that's going to decrypt to theta 1 minus A times theta 2, and H to the minus B times V. But again, by definition, V is H to the B, so that's going to give you 1. Okay, and 1 paired with anything gives you 1. So that also just disappears. And finally, when we decrypt this matrix here, 111T, well, all the 1's raised to something, and that's just 1. So that's going to decrypt to T. So now we know this verification equation holds, and therefore, if we decrypt it along the columns and along the rows, we should get the same thing on both sides. Okay? On the left side, we get the pairing of x, y. On the right side, we get 1 times T, So we get the conclusion that the pairing of x with y is actually equal to t, which is exactly what we wanted. So that gives you perfect soundness, guarantees that the pairing of x and y is actually t. And it's actually stronger, it's a proof of knowledge, right? Because if you knew this secret exponents a and b, the discrete logarithms of u and v, or the Gamal decryption keys, right? Then you can actually decrypt the ciphertext. You can get out x, you can get out y, and you're guaranteed that the pairing of x and y is equal to t. Yes? You really get x and y, because you can, let me just go back one slide here. So I was simply defining, so I would, if I decrypt C1, C2, then I'm in G1, in source group 1, and that will give you x. And D1 and D2 live in source group 2, and that will give you y. And that's the ones that you will be extracting if you have the extraction keys. Okay? So the intuition really here, then what is the intuition behind the scheme? Okay? So if we look at this one here, right, the idea is that GU, if you decrypt that along the column, it's just going to give you 1, right? Because it's a trivial El-Gamal ciphertext. Okay? And that's sort of the justification, why would I decrypt along the columns? Because whenever I have GU and I decrypt that along the columns, it just goes away. Okay? And the same thing with this ciphertext here, if I decrypt that along the column, it's going to give me the encrypted X. And what about decryption along the rows, right? If I decrypt this one along the rows, it's just going to give me 1. It cancels out. Okay, if I decrypt this along the rows, it'll give me the secret plaintext Y. So really the way you should read this verification equation, right, is it's a way to set up a system such that essentially the proof elements get paired with something that's 1, that kind of cancels out. And the other proof elements are paired with something that's also 1, that just cancels out. So the only interesting thing left are the ciphertext here that encrypt x and y, and the target element over here, right? And that's where we get the matching. Why is it that the pairing of x and y, the secret plaintext, is t? That's because these are the only 2 parts of the verification equation that contain some interesting information that doesn't trivially decrypt to 0. Yes? Right, so why can you justify that anybody would know A and B? And in some sense, you cannot, right? I mean, so in normal operation of this proof system, you would hope for, again, some trusted third party comes along and says, here is a setup, a type 3 pairing, and here's some generators G and H, and trust me, they're good. I'm coming from NIST, and you know, everybody loves NIST and so forth, right? And then the trusted third party will also say, and by the way, I know that you need some El-Gamal encryption keys, so here is a public key U, and here's a public key V, and you know, go ahead and use those, right? And if you trust the trusted third party, nobody knows anything else, and that's the setup that everybody is working with, right? Now, if you then go into, you know, you are building a cryptographic protocol, you need a security proof, right? Then we know in security proofs, sort of like, we imagine, you know, the things might be a little different, okay? And in this case, you could imagine, okay, now let me see, do I actually really get soundness and so forth, right? And, you know, what if I actually knew that this trusted setup was A and B? So I think you should think of these things as, you know, zero-knowledge simulation as being in some slightly tweaked world where, you know, you get a simulation trapdoor. And A proof of knowledge is also a slightly tweaked world where, suddenly somebody does actually come along with this extraction key, right? And it's something you can use when you do cryptographic security proofs, but typically would not be available to anybody in real operation of the system. Yeah. Exactly. So that's what I mean. Yeah. So yeah. So decrypting along down the columns is you take the first row, you raise it to the -a, and you multiply that to the second row, and now you have one row. Okay, so let me go back. So I think if I paraphrase now, I don't remember my own words that precisely. But I think what I said was, okay, if we look at these, so here we have 4 2 times 2 matrices, right? That's a verification equation that the verifier checks holds as true. Okay? And what I'm saying is, if you do these sort of decryption of along the rows, so in other words, you take the first row to the -a times the second row, you get a row, then you do sort of the first element to the -b and multiply it with the second element, you get one group element on both sides of this equation. And my claim then is that the group element you get on the left-hand side is the pairing with x with y. I think it ends up being a unique solution. I mean, this ciphertext here has a unique plaintext inside, and this ciphertext has a unique plaintext inside, and that's what you would be decrypting to get you. So once these elements are all known, then there's a unique value you get by decrypting on both of these directions. Sure. Any other questions? Yeah?
So that seems interesting. I also looks like these papers, you allow the knowledge extractor to track door.
Mm-hmm.
Right? This was, and it seems like the new start, like if you're thinking 16 and the QA piece that the knowledge extractor doesn't need the track door. Your knowledge signature.
Right, yeah. So this is sort of like very different from the snark world, right? Because in the snark world, you have proofs that are much smaller than the instance and the witness that you're actually trying to prove something about. So information, theoretically, it would just be impossible to encode the witness inside that kind of short thing. So whereas here, we are essentially encrypting the witness, right? And we're just saying, okay, and if you know how to decrypt these ciphertexts, then you would get out the witness. Okay, so what you get when you compare those two types of proof systems, you would get larger proofs because they are big enough to contain the full witness. But on the other hand, they rely on sort of like very mild knowledge extractor, sort of LGML encryption, DDH, that we all know and love, right? And that suffices to decrypt the ciphertext, get out the witness. Whereas in the snark world, you have to do something else to extract the witness because it's not there. Information, theoretically, it's just not available in the proof. So there you sort of like have to go into the prover's head and sort of see, I could somehow extract from the prover directly what the witness is. Okay. Okay, so this is something that we can generalize to more complex equations. Okay, so in general, we may not just have a pairing of x and y and be interested in whether that gives us a target element t, but we would have a pairing of knowns with unknowns and unknowns with knowns and unknowns with unknowns, and that would give us some target element. And but the idea is exactly the same. The prover would LKML encrypt every single variable, and then the prover would compute for every equation a proof, which, when you have this more complex equation, gives you these more complex ways, but it's still exactly the same kind of things that are happening here, right? You still have some randomization in the end, so you get some random proof elements, and you still get for every equation just 4 proof elements, pi1, pi2, and theta1, theta2. Okay, and you can do this kind of generalization for many types of equations, but I think this is a good time to take a break.